Hello, North Tahoe High physics students. We're going to go through a quick video today, at least I hope it's quick, to derive the kinematic equations, the equations of motion that we are going to be using and practicing in class for a couple days. So there's two forms of motion that we've studied so far. One of them is constant velocity motion, and the lab that we did, if you remember, way back when, was with those carts that just moved at one speed across our markers of the tape. The other one was uniformly accelerated motion. That means that the acceleration itself is constant, so it's speeding up the same amount or slowing down the same amount every second. And we explored those with the carts on the tracks and the motion detectors. So we're going to use the ideal graphs that came out of those to study kinematics. But it's really important to remember that the equations that we end up with here came from first simple observation, position and time, then graphing them, and we'll review the graphs, and then the equations come from the graphs. So that's the order that physics works. It never starts with equations first. So let's take a look at a pretty typical graph for constant velocity motion. I'm just going to say we're going to start it right here, and should first of all put units on here, right? This is usually what we call x versus t. X would be a position in meters, and t is a time in seconds. This was v, meters per second, or velocity versus time in seconds. Constant velocity motion had a straight line on x versus t, and that meant, remember, that the slope of that line becomes the value of v versus t. So we have something that looks like that. To remind ourselves what we wrote for this, or what we remembered, the slope of this graph had units of meters per second. So what that meant is the slope was velocity. And the area of this graph had units, right? If I do the dimensional analysis, meters per second times seconds, had units of meters, which is our units for displacement. Okay, so there it is, just cleaned up a little bit. We're looking then at the linear function of x versus t and realizing, hey, it's a line, so it has to fit the form y equals mx plus b. We talked a little bit about this. What is b, the intercept? That is your initial position, xi. We've been over the fact that m, which is generic speak for slope, in physics for this graph is velocity, and the x-coordinate is time. So we've already found our first kinematic equation. The position can be calculated by this equation. If you know where you start and your velocity and how long you're traveling at that speed, you can predict or calculate where you're going to end up. Let's take a look at the other one. Remember this one, the area has meaning, and it's not a literal area. We got to look at the units. The units are area units of meters or displacement. So when I look at this one, here's it's just a rectangle, so it's pretty easy to calculate. Here's a value v, and that v is constant over this time. So what I get then is v times this time span, delta t, equals delta x. And actually, if I expand that out, remember what delta x is? Delta x is xf minus xi equals v delta t. And I could just add xi to both sides. That would cancel that out, and I get that. So let me clean it up. xf equals xi plus v delta t. These are the same equations, and it's kind of interesting. It's the one equation we have for kinematics, and we'll explore that a little bit more tomorrow. One equation for constant velocity kinematics, rather. But it's kind of cool to see that the area of one, the area of v versus t, actually tells us the function or the equation for the line on x versus t. So we're going to see that and go use those ideas and go a step forward with uniform accelerated motion. Okay, so let's take a look. Sorry about that. Let's take a look at uniformly accelerated motion. So we'll consider only the case where it's accelerating in a positive direction. If you remember that, position versus time was no longer a straight line. It was a slope whose curve is progressively becoming steeper and steeper. Velocity versus time was no longer horizontal. It could have been a kind of a little bit of curve, a straight line with a slope, but uniformly accelerated motion means we do have constant acceleration. So again, remember, still the same thing holds true. The slope of the graph above becomes the value of the graph below. So these were typical of something uniformly accelerated. We won't start analyzing to find the kinematic equation for this curve because most students, beginning students, would have a real hard time figuring out how are we going to find out that. We understand linear stuff, but that curve might be harder to fit exactly. So we're going to start our investigation of the equations looking at v versus t and remembering some of those things that we've learned. So we're going to start this analysis by remembering that v versus t, the area under that graph, tells us the displacement. So if we can find the area, we can find the equation for displacement or change in position. So this is a straight line. It's not going to be too difficult. We're actually going to divide this shape up into two easily recognizable shapes. There we go. A rectangle and a triangle. So let's look at the rectangle down below. Base times height, real simple. Velocity is constant, as this value is your height, and your base is some span of time, delta t. So remember, this right there is vi. So the area here would be vi times delta t. Let's look at the triangle. The triangle is simple in geometry. We know it's 1/2 base times height. Okay, so let's take a look. The 1/2 is pretty simple. We're just going to keep that 1/2. The base of this triangle is the same time span, delta t, but the height we need to explore a little bit. The height is a change in velocity. And we know the slope of this graph is a change in velocity over a change in time. So height is actually delta v, and if I divide or multiply both sides by delta t, I get delta v equals a times delta t. So this is my height, delta v. I'm going to substitute that in, a delta t. So I get this equation cleaned up a little bit for the area of my triangle. So that's what it looks like. I'm going to go ahead and write the entire equation out. We said the area is displacement, that's delta x, and it is composed of two areas, vi times delta t of the rectangle, plus the 1/2 base times height, but in our variables that can be expressed as 1/2 a t squared. That is a very important kinematic equation. Sometimes you'll also see it expanded out so that it looks like this, where I expand out the delta and it might look like this, but they're the same equations and we can use them the same way. Okay, and we have then one more equation to find out then. We use the area of v versus t to find the displacement equation, the equation for that curve. Now we're going to find the equation for v versus t, period, just that line. And that's simple. It's y equals mx plus b. So we're going to solve y would be a v. The m, or the b, the intercept usually, it would be vi, our starting velocity. The m, the slope of this graph, is acceleration, so instead of m we'll use a. And then of course the x in y equals mx plus b is time. So that's our second kinematic equation for velocity, for uniformly accelerated motion. We won't have an equation for acceleration because it will always be constant for our class. Okay guys, so here they are. This is what I'm going to check for your reading tomorrow. Can you show me these equations? And it looks like there's a lot of them. All the blue equations for constant velocity are the same thing, so any form works. All the red equations for displacement or position with uniform acceleration are the same thing. So either one of those works. And the green equations for velocity for uniform acceleration are all also the same thing, just cast in different ways. There is one more equation that we can use. All of these involve time. It might be nice to have something that doesn't involve time. So the last equation I'll ask you for is this. So here's a way that we could develop an equation that would get rid of time. So if we didn't have time but we had some other information, we might be able to solve for some kinematic variables. What I'm using here is the displacement equation from the screen before and the definition of acceleration, and I'm solving acceleration for time. So I can use this expression for delta t and plug it in there. And I'm not going to do the full thing. It's not that difficult, but there's a lot of order of operations, and it's really easy to lose a sign. I'm just going to tell you the end product, and if you're interested, ask me, and I can get you started and show you how it happened. So after a lot of algebra, you end up with this, our last kinematic equation. So again, on our homework check tomorrow, I'm going to ask you just to state the kinematic equations in one form or another for constant velocity and uniform acceleration, and we will work with them and actually use them together in class. I know no one's going to be an expert on them right away.